Hello, this video is for chapter 2.3 part 2, dealing with calculating limit analytically when the substitution rule does not work because you have a denominator 0, but at the same time it's not 0 over 0. It's not an indeterminate form. If it is 0 over 0, we know that we can cancel a factor or simplify complex fraction to get on with the limit, but it is not 0 over 0. So there are cases where you have, a number which is not 0, like a over 0 minus b over 0, where a and b are both just a constant. And so what would be the limit? So we're dealing with that first, and then later on we'll deal with the case where we have just one number, k over 0. So if we do direct substitution, I have k over 0. So what do? There's no common factor to cancel. So if we have these types of things, a over 0 minus b over 0, actually plus and minus, what we can do is we can combine them. The fact that they're both 0 meaning that there is a common factor, and we can actually add them or subtract them by combining them into one single rational expression. So this is the example. I have limit x approaches 0. I want to do 1 over x plus 5 over x minus 5. If we plug in 0, this will become 1 over 0 to become 5 over 0. So what is the limit then? It can simplify, can cancel. So what we do is we would do common denominator for this fraction. We would multiply x minus 5, top and bottom. So it has the same denominator for both of them. And then if we add them, this would become x minus 5, 1x minus 5 plus 5. And you can see immediately this cancel. And then we have x over x minus 5. This can now cancel because this is a product. And now we have only one term. So I can change this limit into x approaches 0, 1 over x minus 5 only. I'm replacing it with another function that is not defined as 0, but which does not matter because when we are finding limit, we don't care if x equal to 0 is what. So now when I do direct substitution, it would work. So it would be equal to 1 over 0 minus 5, meaning negative 1 over 5. So if you have like a few over 0 terms, just add them. And sometimes it works. So we can try this next in class. The caution is don't just multiply them. You should factor any quadratic term first to see if there's any common factor. But we'll work it in class. The second one is when we only have one term, k over 0. So just like this one. When we plug in 2 from the negative side, the bottom becomes 0. It will be 4 minus 4 is becomes 0. But the top is direct substitution. Become 2 minus 3 over 0 equal negative 1 over 0. So I cannot add anymore. It's just one term. So what do? So what happened is the strategy is to separate a 1 over x minus a to the n from the rest of the function. Based on the fact that if I have one number, k, maybe not, I should not use k. Yeah, I can use k. K times infinity is still infinity, right? If k times negative infinity is still negative infinity. In this case, k is positive. Now, if k is negative and I do a negative k times infinity will be negative infinity, k is positive. Okay. If k is negative, then we have reverse. So meaning that if I can split it into two functions, so I can actually use this fact to see if it goes to positive or negative infinity. This would most likely go to infinity, but is it positive or negative? We'll split it up into two parts. So let's look at x minus 3. We are looking at, because x approaches 2, we are looking at x minus 2 terms. We are looking at x minus 2 being in the denominator. And when we factor out, we see 1 to the power 1 x minus 2 here. So the rest will be split out. times 1 over x minus 2. Okay, so we will do each limit individually. If I do limit x approaches 2 minus x minus 3, x times limit x minus 2, 1 over x minus 2. Do you remember in 2.2, we know how to do this? We say that this either shoot up or shoot down, depending on if you're doing from the left or right? So 2 minus means you have a low 2. That means you have a one small negative. So this would go to negative infinity. That's how we figure. And this would just do direct substitution. 2 minus 3 is a negative 1 over 2. So it's a negative 1 times negative infinity, right? 2 minus 3, yes. So that would be positive infinity. So that's the answer. So let's do this one. Oh, maybe we can just isolate them. So we can see x minus 1. If I plug in direct substitution, I have 3. But the bottom would be 0. So this is something that we don't know if it's positive infinity or negative infinity. So what we do is we would just do x plus 2 split up times 1 over x minus 1 square. How do I know that this is the one? That's because I'm having x approaches 1. So this is the one that we know how to calculate in chapter 2.2. So we will do x approaches 1. So this becomes 3. And when x approaches 1, no matter it is positive or negative, you square something, this is going to be a small positive number. This would be infinity, right? Because this is 1 over small positive. From the positive side or the negative side, when you square some number, it's small positive. So it's 3 infinity, so it's still infinity, a positive infinity. So then the next thing, so this would cover all the rational and polynomial cases. And the next things we want to deal with is trig function. So we haven't have any limit law that apply to trig functions. Can we just do direct substitution? Is there any things that we can do if we are doing trig functions? So there is actually 2 skills. So particularly if you have a function of trig function that go with multiply with a polynomial function. So we would use something called the Squeeze Theorem. Okay, the Squeeze Theorem. Let me make this a little bigger. So limit of trig functions, the Squeeze Theorem say if we have 3 functions, the middle function is always between f of x and h of x. So let me see if I can find the book that talks about the Squeeze Theorem. They they have a very good 2.3 here. Yeah, the Squeeze Theorem here. So I have one function is h of x, I have function f of x. G of x is always between them, but when they approach a, both h and f, the 2 functions that is between, that is the top and the bottom of g of x, there's always both of them approach L. And then we can say that g would also approach L. The g function would approach L. So the picture shows that very clearly that if you can find 2 functions that is always between g of x, or g of x is always between them, and then at the same time this 2 function has a limit at x approaches a, then we can find the limit of g of x. Okay, so let's go back to that notes that we have. Okay, so let's find. So when we use the Squeeze Theorem, the work is not actually to calculate the function, but actually to find the function that is always less than, one function that's always less than g of x, and one function always that's bigger than g of x. So in the above case, we say f of x is the smaller one. Okay, so we say we want to find limit of x squared sine x, limit x squared sine x, and there's no limit law that allow us to do that. We know the limit for sine x. When they're close to 0, they are 0. You can look at the book, they actually deal with it. But when we multiply them, can we do that? So what happened is we would define a function f of x equal to negative x squared. And h of x is equal to x squared. So now we know that sine x is between negative 1 and 1. So if we multiply both sides, and x squared is positive, if we multiply a positive number on an inequality, that would always work, right? So this would be our hx, and this negative x squared would be our fx. And it turns out that my function that I want to find limit on would always be between these two functions. But at the same time, because this is a polynomial function, if I have x approaches 0, negative x squared, so that's just equal to 0. And then limit x approaches 0, x squared is also equal to 0. So by the Squeeze Theorem, limit x approach 0, x squared sine x would also equal to 0. So this step is the Squeeze Theorem. So most of the work you do is to define the two functions. And whenever you see this sine x or cosine x that multiply with polynomial, you would know these facts, and these facts will let you define your two functions. The next things that we always use is a function. Is a limit that we want to establish. That is limit x approaches 0 sine x over x. When you do your classwork, I think I asked you to do this by a table method, that it should equal to a number. I don't know if you remember, but here we will prove it, and we'll use it to find some limit of trig function. So this one is really, really useful. So what is the proof? The proof is actually in the book also. There's a more complete proof. But in a nutshell, it goes like this. If I have a unit circle, and this is sine x, because y is sine x, right? And this is theta. So this is theta. But then, oh gosh, I draw it really small. And then the line that goes from the edge of the circle top is tangent theta. Maybe I'll show the book. It's about, below, here. So this is tangent theta, this is sine theta, and this is theta. Because theta is a radian, is actually the arc length of the unit circle. So you can obviously see that theta is between sine theta and tangent theta. So what we will actually just show it. So I'm going to just write it down here. So in a bigger picture, you can say theta is between, sine theta is the shorter one, right? And tangent theta is the one that is outside. And then because if I divide both sides by sine theta, I have 1 less than theta over sine theta less than 1 over cosine theta. And we can switch it around. You would have cosine theta, switch the reciprocal of it, equal to sine theta over theta less than 1. And if we take limit for all of this, x approaches 0 for cosine theta would be between limit x approaches 0 for sine theta over theta and less than limit x approaches 0, 1. And of course this is 1, and this is also 1 when you plug in cosine theta. Cosine 0 is 1. So that means this is also 1. So limit x approaches 0 sine x over x is equal to 1. And this is very important.